Fierce functions is to protect the circuit from excessive currents and the circuit gets too hot. This usually happens for two reasons. First, short circuits due to worn insulation, and second, overloaded circuit. A fuse is always connected in a live wire is a short and thin wire with low melting point. When the excess current flows through and causes the circuit to heat up past a certain threshold, the thin wire in the fuse melts, thus cutting the current flow. Without a fuse, overloaded circuits will continue to heat up until a fire happens. The rating of a fuse is shown in amperes A. Fuses with rating of 3A means that it should be used in a circuit that should not have current exceeding 3A. If the current flowing past the circuit is 3A or higher, the fuse will break. Trip switches, which is circuit breakers. Circuit breakers function the same as fuses, but they are reusable. When the current exceeds the rated value, an electromagnet will disconnect the circuit. They are usually more adventurous than a circuit because they are faster and reusable, but they are larger in size. So, earthing. The ring main has a third wire called the earth wire. It is connected to a metal water pipe or to an earth connection on the supply cable. It is there to act as a precaution to prevent electric shocks and when should the appliance falls. The earth pin is connected to the appliance automatic case so that any leakage of current into the case will immediately travel into the earth, preventing the metal case from turning into a live wire which can electrocute on contact. Double insulation. Most electrical appliances are double insulated, where the inner circuit is encased by a plastic outer case to prevent accidental direct contact with the circuit. Moreover, the handle of appliances such as hair dryer or vacuum cleaner are wrapped in plastic insulator for extra protection. Electromagnetic effects. When a current-carrying conductor is in a magnetic field, it will produce a force. The force is due to the interactions between the magnetic field of the permanent magnets and the magnetic field produced by the current-carrying conductor. When the direct current power supply is turned on, the conductor will move due to the interactions between the magnetic field of the permanent magnet and the magnetic field produced by the current-carrying conductor. When the direct current power supply is turned on, the conductor will move due to the interactions between the magnetic field of the permanent magnet and the magnetic field produced by the current-carrying conductor. Catapult field. The field that causes the movement of a current-carrying conductor to move in a magnetic field is called a catapult field. When a current is passed through a conductor, typically a wire, a magnetic field will be formed around the wire. The directions of the magnetic field follows the right-hand grid rule. The magnetic fields that oppose one another will become weaker. Direction of the current self-plane to paper is a dot, and across its direction of current into the plane of paper. When a current is passed through a conductor, typically a wire, a magnetic field will be formed around the wire. The directions of the magnetic field follows the right-hand grid rule. The magnetic field that oppose one another will become weaker. The interactions between the two magnetic fields will ultimately produce a resultant force, with one side of the wire having a stronger catapult field than the other. This difference in catapult field causes the current-carrying conductor to move towards the weaker region. This motion follows the Fleming's left-hand rule. The interactions between the two magnetic fields will ultimately produce a resultant force with one side of the wire having a stronger catapult field than the other. This difference in catapult field causes the current-carrying conductor to move towards the weaker region. Right-hand grid rule. The right-hand grid rule is used to determine the directions of a magnetic field produced when a current flows through a wire or conductor. The thumb points in the directions of the current flow. The other fingers, when curled out, will represent the circular directions of the magnetic field produced. The Fleming's left-hand rule. It's used to determine the directions of the forced motion when a current-carrying conductor is placed inside a magnetic field. It's used to determine the directions of forced motion when a current-carrying conductor is placed inside a magnetic field. The F is the thumb points towards the directions of motion force. The index finger points towards the magnetic field from north towards south. The middle finger points towards the directions of the current flow. Factors affecting magnitude of the force acting on the current-carrying conductor, magnetic field. Magnitude of the current, generally the larger the current, the larger the force produced. Ways to increase the current is firstly increase the magnitude of the electromotive force. Use wire with lower resistance. Use a coil instead of a single wire. Increase the current. Increase the magnitude of the electromotive force. Use wire with lower resistance. Use the coil instead of single wire. Strength of magnetic field. Generally, the stronger the magnetic field, the larger the force produced. Ways to increase it is by using a stronger magnet or place magnets close to each other. Turning effect of current carrying coil in a magnetic field direct currents. A direct current motor in an electric fan uses the effect of catapult field to cause the motor to spin continuously when a current is passing through it. A line of wire is bent into a coil shown in figure above where current can flow from A to B to C to D. Using the Fleming's left-hand rule, we can determine the motions of the coil. Working principles of direct current motor. The direct current motor is found in many electrical devices that consumes low amount of power, such as a toy car or mini fan. Current flows through the loop DCPA. According to Fleming's left-hand rule, the current flow in the coil causes the force to act downwards at DC, where the force acts outward at BA. The force causes the coil to rotate clockwise. When the coil is in a vertical position, the current flow is interrupted because the common brush does not touch the commutator. However, the coil is still rotating clockwise due to the inertial effect. The coil continues to rotate until the current flows reversely through A, B, C, and D. According to Fleming's left-hand rule, the current flow in the coil causes the force to act downwards at AB and outwards at CD. This causes the coil to continue rotating clockwise. This is the same as second scenario. The coil then returns to its original positions and then the cycle restarts. The rotation speed of a direct current motor depends on, firstly, the number of turns of wire coil, the magnitude of current flow to the coil, the strength of the magnetic field. Electromagnetic induction. Electromagnetic induction is a phenomenon of inducing an electromotive force across the wire cutting a magnetic field. It can be thought of as the reverse of a motor when motor converts electrical energy to motions. A generator uses electromagnetic inductions to convert motions into electrical energy. Moving a conductor in a magnetic field. Moving a wire quickly upwards, the point of the galvanometer deflects to the left side. Current is induced. Moving a wire quickly downwards, the pointer of the galvanometer deflects to the right side. Current is induced. Moving a wire parallel to the wire and perpendicular to the magnetic field. Pointer does not move. No current is induced. Moving a wire parallel to the wire and perpendicular to the magnetic field. Moving a wire parallel to the directions of the magnetic field. Pointer does not move, no current is induced. Besides the straight wire, electromagnetic inductions can also occur in a solenoid coil wire. When the bar magnet is pushed quickly into the solenoid, the pointer of the galvanometer is deflected to one side, indicating that current is induced. The same also happens when the bar magnet is quickly pulled out, only this time the pointer of the galvanometer deflects to the other side, indicating that current is produced in the opposite direction. The same also happens when the bar magnet is created, but only this time the part of the galvanometer differs to the other side, indicating that current is produced in the opposite directions. Logically speaking, if the bar magnet stays stationary while the solenoid moves towards or away from the magnet, can also induce a current. Faraday's law states that the magnitude of the induced electromotive force is directly proportional to the rate of cutting of magnetic flux. This means that electromotive force can be increased by increasing firstly the speeds of relative motion, second the number of turns of coil, third the strength of the magnetic field. Directions of induced current in straight wire and solenoid. Use Fleming's right-hand rule to determine the directions of induced current. Lenz's law is used to determine the directions of induced current. Lenz's law states that the induced current always flows in the directions that opposes the change of magnetic flux that causes it. For example, the thumb is the force motion, the index finger is the field, and the middle finger is the current. Firstly, magnets move towards solenoid. Second, induced current produces a north pole to repel the magnet coming towards the solenoid. And then, firstly, magnet is moved away from the solenoid. So second, induced current produces a south pole to attract the magnet moving away from it. Direct current generator and alternating current. These are the two types of generators: direct current generator, alternating current generator. Voltage generator, direct current is just tree like that, and alternating is like a sine curve. Direct current generator. A direct current generator consists of coil mounted on an axle between the poles of magnet. There are commutators at both ends of the coil, while two carbon brushes are connected to output such an electrical device. The brushes are connected to commutators loosely. Coil structure on the axis is rotated so that there is a magnetic flux cutting and thus produce an induced magnet-induced electromotive force. A direct current generator consists of coil mounted on an axle between the poles of the magnet. And a direct current generator consists of coil mounted on an axle between the poles of magnet. There are commutators at both ends of the coil, or two carbon brushes are connected to output such as electrical device. The brushes are connected to commutators loosely, and the coil structure on the axis is rotated so that there is a magnetic flux cutting and thus produce an induced current and induced electromotive force. Coil structure on the axis is rotated. Mechanisms of direct current generator. Firstly, when the coil is in vertical position, the sides of the coil move in parallel with the magnetic flux. There is no cutting of magnetic flux. Additionally, the carbon brushes do not touch the commutator. When the coil is in a horizontal position, the sides of the coil will move perpendicular to the magnetic flux. Cutting of magnetic flux occurs. The carbon brushes will then touch the commutator. Induced current is produced. Using Fleming's right-hand rule, current flows from side A to B. When the coil is in vertical position, the sides of coil move in parallel with the magnetic flux. There is no cutting of magnetic flux. Additionally, the carbon brushes do not touch the commutator. When the coil is in horizontal position, the sides of coil move perpendicular to the magnetic flux. Carbon brushes touch the commutator. Induced current is produced. Cutting of magnetic flux occurs using Fleming's right-hand rule. Current flows from side B to side A.